Good afternoon, folks. We are super lucky today to have Grace from Meta joining us as a research scientist in the display system research team. She works on novel display and imaging technology for virtual and augmented reality. She's particularly interested in the joint design of hardware and algorithms for imaging systems, and her work spans optics, optimization, signal processing, and machine learning. Co's recent work on Flamera, a light field camera for virtual reality pass-through, won Best in Show at SIGGRAPH, Emerging Technology Showcase, and she received widespread positive press coverage from venues like Forbes and Upload VR. Co earned a BS from Washington University and her PhD from Berkeley in the UC system, advised by Laura Waller and Ren Ng. Over to you, Grace. I'm looking forward to this.
All right, thank you so much. I'm super excited to be here, and thank you for the wonderful introduction. As was just said, my name is Grace. I'm a research scientist at Meta, where my research focuses on novel displays, specifically for head-mounted systems like augmented and virtual reality. Today, I'm going to be talking about a topic that I've gotten really interested in lately, which are holographic displays, which I love because they have the ability to make these stunning 3D or even 4D images in a really compact form factor. When you first think of a hologram, you might imagine the sort of glowing blue 3D figures that were popularized by Star Wars. This is not really what I'm going to be talking about today. Building a display like this would be quite challenging, because if you imagine you have a projector off to the side, well, light travels in straight lines, and if we don't have anything there, if we're just projecting this into free space, how's that light going to bend so that a user to the side can see it? However, even though a display like this doesn't really exist today, actual holograms that do exist can be just as magical. So here's a video of a real hologram. This video clip was taken from a recent 3 Blue 1 Brown video on holography that was really excellent. And you can see that this image of a microscope is contained on this thin 2D sheet, but it captures all of these really realistic 3D cues. It really looks like it's popping out of the page. There's complex view-dependent effects and focal cues, as though that microscope were really there. I think images like this are a lot of the reason why I and other people working in holography are really excited to pursue this field. So how does this work? Holograms are based on the wave nature of light. So today we're going to be thinking of light as an electromagnetic wave. As I'm sure everyone in this audience knows, there are a few properties of waves that we care about. The wavelength represents the color of the light. But today, we're not going to worry about that. We're going to assume we're dealing with monochromatic light only. The amplitude is the brightness or the intensity of the light, and this is what we're usually measuring in a standard photograph or emitting in a standard display. Then there's the phase, which is sort of the offset of the wave, how far we are within the wave cycle. Phase isn't something that we can see or measure directly, but it contains a lot of useful information about what's happening in the electromagnetic field. To give a bit of an intuition about that, let's imagine that we have a wave that's traveling in perpendicular towards a plane. This wave has constant phase over the plane. Basically, the plane is seeing the same part of the cycle of the wave. But when the wave starts to come in at different angles, we see more and more phase variation at this plane. So loosely, I like to think of the phase as containing information about what direction a wave is propagating in. You can already imagine that that information is going to be really useful when we're trying to recreate 3D images. More abstractly, if we have some arbitrary image, like a microscope or some other object, that we illuminate with a laser, that light is going to hit the object and bounce around. It's going to interfere with itself. It's going to reflect off of the object, creating this really complex electromagnetic field pattern. However, even though this is really complex, we can still characterize it by a phase and an amplitude at every point here. Our goal when making a hologram is to try to capture and replicate that amplitude and phase. Of course, the phase is a really important part of that information. The amplitude alone is not going to allow us to recreate the image. And as I said before, phase isn't something we can see or measure directly with existing materials. The insight into how to measure and capture phase information was invented by Dennis Gabor back in 1947. And he wasn't trying to create a novel display system or make cool holographic art, but instead he was trying to improve the resolution of the electron microscope. So electron microscopes were tantalizingly close to being able to resolve atomic lattice structures, but weren't quite there yet, because if you kept the aperture small enough so that there weren't aberrations, the diffraction limit made it so that there wasn't enough resolution. But if you opened up the aperture to the point where you'd have the needed diffraction limited resolution, aberrations were so severe that the resolution was blurred out once again. What Gabor realized was that he could keep the aperture open, and if he could measure and record the phase information, he could correct for these aberrations in post-processing. So he set about trying to come up with a way to record the phase, and what he suggested is something that seems pretty obvious in retrospect now, because it's been like 65 years or something. And what he proposed was adding in a second wave, a reference wave, to create an interference pattern with the first wave. So when the two waves have lined up phase, they're going to have constructive interference, creating bright spots. And when they're anti-aligned, they'll get destructive interference to create dark spots. And this essentially translates the phase information into intensity information that we can actually measure and record. Gabor called this image of this interference pattern a hologram, based on the Greek prefix hol, meaning that this captures all of the information in the image. His initial holograms looked something like this. You can't really see what the object is here, but this hopefully captures all of the information you need in order to reconstruct the object and do things like aberration correction. These days, we would take an image like this and do some sort of digital processing to try to reconstruct the image. But back in the 40s, this was all done in analog. So what Gabor showed was that you could take this exact hologram that he measured and re-illuminate with the reference beam and create a version of the object. This is pretty cool, but Gabor was a bit ahead of his time because when he came up with this invention, there weren't bright and coherent enough light sources to really enable the full impact of holography. He published his paper, there was a few follow-up works, but then it was largely abandoned. He even said later about a follow-up project that the response of the optical industry to it was so disappointing that they did not publish a paper on it for 11 years. So a bit of a downturn in the history of holography, but luckily for everyone, the laser was invented in 1960, which was a bright and coherent enough light source to enable a lot more applications in holography than even Gabor had originally thought of. In the end, this resulted in Gabor winning a Nobel Prize for that idea that he had largely abandoned several years prior. So if we go back to our microscope hologram, the way that an analog hologram like this is made is pretty similar to what Gabor originally proposed. We have our complex electromagnetic field that's radiating off of our object, and we're going to shine in a reference wave, some other wave of the same wavelength, that's going to cause interference between these two waves. So we'll get bright and dark patches when we have constructive and destructive interference, and we can put a photosensitive film here. A lot of times in holograms, we actually use something that, while thin by normal people's standards, is thick compared to the wavelength of light. So we can print many wavelengths within this. And so then we have this printed pattern from these two electromagnetic fields. Like Gabor showed, we can then illuminate with the same beam as the reference, and when the light interacts with all of these fringes, it's going to diffract off of them, and the result is the same electromagnetic field as though the object were really there. And this means that even just looking at this thin film, we're going to see the illusion as though that object were truly present, complete with all of these 3D cues. And so this, of course, is how we get these beautiful images like I showed you before. Now, I sort of went through all of this history, and you might be wondering, what else is there to do? This was all solved like 60 years ago. We've made these beautiful images. These are in museums around the world. There's a lot of lovely art that's based on holograms. What's next? Well, I'd like to see holograms like this become a true display technology. This is the equivalent of a photograph. It's static, we can't change it over time, and it had to be printed from a real 3D object. Ideally, we'd like to have displays that we can dynamically control and that we don't need to physically have an object present in order to print them. We'd like to be able to make displays directly from digital content, like computer-generated graphics or even text, and be able to display that without physically instantiating it. So with that, enter the world of computer-generated holography. To go from an analog hologram like this to a dynamic computer-generated one, there's two things we need to change. First, we need a controllable way to modulate the light. So instead of using a static film here, we're going to replace this with a display panel, which in holography we call a spatial light modulator, or SLM for short. This is basically because it's going to change the light over space. You can think of most displays as some form of spatial light modulator. I guess this is just jargon that we like to use. However, in holography, instead of modulating the amplitude or intensity of the field, we actually frequently choose modulators that control the phase of light by either using liquid crystal or MEMS devices to control the optical path length at each of the pixels. So with this, we now have a way where we can dynamically control what we're showing. The other component that we need is the computational side, where instead of physically interfering an object in a reference beam, we're going to do this computationally. We're going to simulate what's happening in the system and then use that to drive our display. So with this, we can hopefully computer generate our holograms and create a dynamic display. But both of these changes are kind of fraught. On the simulation side, we've got pretty good models of how light propagates and interferes, but it's really hard to match all of the details about what's happening in the real world. So just as an example, if we simulate the interference between some reference beam and an object beam, but then our real illumination doesn't match that reference beam in real life, what we see from our display is not going to match what we actually got in our simulation. It turns out that holograms are really sensitive to a lot of non-idealities, like optical aberrations and even dust, which can be really hard to accurately capture in a simulation and model so that it really matches the real world. One of the things that actually creates a lot of these non-idealities is that spatial light modulator itself. There's a lot of discrepancies between what we can do with a dynamic digital panel versus a static film. One of the most obvious differences is the resolution, where film can be super high resolution, and the features that we're trying to print are generally on the order of the wavelength of light, so that's hundreds of nanometers. But the best spatial light modulators today have pixel sizes on the order of a few microns, so that's an order of magnitude larger than the resolution that we really want to be showing in these systems. In addition, these panels are modulating light at a single plane instead of over a small volume, and so this further limits the degrees of freedom that we are able to control in these systems. And finally, these things just rarely act ideally. They might have limited bit depth, they might exhibit crosstalk between the pixels, so the pixels don't actually act independently of each other. There could be just non-idealities in the response of this as you change the voltage, and a lot of times they have limited diffraction efficiency, so some of the light doesn't get modulated at all. So, with all of these changes, it becomes a really big research problem to figure out how we can get that image fidelity and beauty of analog static holograms and turn those into something that's dynamic and controllable. The first dynamic holograms were invented, or I guess shown, in the late 80s. These were out of the MIT Media Lab, and it obviously took quite a while to go from static holograms to something dynamic. As you'd expect, these don't look nearly as high quality as the analog holograms of the same time. I wanted to show some images in this talk, but unfortunately the MIT Media Lab did not respond to my request for permission to use images, so you can look them up on your own though, they're online. It's not really that surprising that these first dynamic holograms weren't as high quality as static holograms of the time. But maybe what's a little bit more surprising is that over the years that followed, despite all the hype about holographic displays, these displays didn't really improve very much. This is a personal and very non-quantitative chart about just general feelings about holography over time. We had a bit of a dip before the invention of the laser when nobody really cared about holography because there wasn't a good way to do it. And we're hitting this second dip where even though we've seen some dynamic displays and there's promises that these are going to get better and better, they didn't really. And to give you an idea of what was happening in that period, let's actually jump ahead to the present day and look at some holograms that I've captured. So this was back in 2021. It was sort of post-COVID, and I'd been doing a lot of working from home and doing a bunch of simulations that were giving me some really nice images like this. And I wanted to go into the lab and start trying these on experimental systems. So when I had the chance to start going back into the office and doing these experiments myself, I was super excited to see what this looked like. But unfortunately, this is the real experimental capture I got from this simulation. So you can see this isn't great. The structure of the image is still there, but this house is corrupted with this speckle noise, which is just visually unappealing and hides details in the image. And I actually think that this image is pretty representative of the image quality that we saw in that 25 years following those first dynamic holograms. This is a really common artifact in holographic displays, so I'd like to take a bit of time to dive into what causes speckle and what are some options we have to mitigate it. So speckle just generally happens when we have laser illumination. This is a picture from the lab where you can see that when we shine a laser on something like this optic, and you zoom in, you can see this characteristic grainy pattern that comes from speckle. Speckle happens because when we illuminate with coherent light, that light is going to bounce off of small microstructures on the object's surface. And these different bounces are going to have different optical path lengths, and when they all come together on your retina or on a camera sensor, by chance, sometimes those path lengths align and we get constructive interference and bright spots, and sometimes by chance they're unaligned and we get destructive interference. And so we get this pretty random speckle pattern that happens in these systems. Here's a simulation of what this looks like. And this actually happens in both static holograms as well as dynamic holograms, because in both cases, we're trying to reconstruct the full electromagnetic field. We're trying to capture exactly what's going on in real life, and real life includes the speckle. Now, this speckle is a little bit less prevalent in static holograms because they generally have higher resolution, so the speckle sizes are smaller and less noticeable. And because of the volumetric nature of the holograms, we have some other options like illuminating with broader band illumination when we replay the hologram, which isn't always an option with dynamic holograms. However, computer-generated dynamic holograms have a pretty key advantage that we can try to use to help with this problem. And that is that this object isn't real. We do not have a physical 3D printed dragon or something that we're trying to print. This is something that's entirely a computer model, so we can alter it in ways to try to make our image quality better. Specifically, we can try to optimize the exact surface structure on this object to try to get all of these different speckles to line up exactly the way we want it to. And this works really well in simulation. So here's a simulation of that process where this is basically what's happening in any algorithm that we use for holographic displays, like a phase retrieval algorithm, is implicitly trying to solve for the phase at the object to get all of those speckles to line up and look really nice. Unfortunately, this is not very robust, and you can kind of imagine we've carefully lined up whether we get constructive or destructive interference, these just sub-wavelength features. So just small movements of the eye or the camera can cause the speckle to reappear. This is also really sensitive to optical aberrations because those also create small path length differences. And I think that that's probably what happened with this experimental result that I showed you earlier. In simulation, all of the speckle is perfectly lined up, but in real life, there were probably some aberrations in the system that weren't captured in the simulation, and that causes there to be substantial speckle in the experimental result. Unfortunately, even if we have perfect calibration, if we knew everything exactly, we don't have anything that's moving, that's non-ideal, this is still a problem if we're trying to create 3D image content. So here's a simulation trying to create a volume of light. So here we see our simulated camera focused on the foreground, now the middle, and now the background. And unfortunately, when we try to create something volumetric, we don't have the degrees of freedom to control the speckle over this whole volume simultaneously. So compared to what we wanted to show in this image, we have a lot of speckle in the simulation, even if we know everything about the calibration perfectly. Since, in general, we would like our holographic displays to be able to show these volumetric effects, this is a pretty big problem. And is really, I think, one of the things that held holographic displays back for a long time. There was a pretty big step change in 2017 with this paper that was published by my now colleague Andrew Mamone. And you can see just looking at these results, comparing his simulation to experiment, it looks a lot better than the ones that I was doing in the lab. The experiment is basically speckle-free and looks pretty much like the simulation. So how did he do this? Well, the idea of this paper basically takes this concept that the object isn't real kind of to an extreme. Instead of optimizing this surface so that we have the same statistics but maybe a different pattern to have better speckle, what happens in this paper is they replace the object surface with this smooth mirror-like finish. Mirrors don't cause speckle. It's really the randomness of a diffuse structure that creates that speckle artifact. And so when we have a smooth surface, all of the light constructively interferes everywhere. And not only that, this is a lot more robust to different optical path length differences because small path length differences don't cause the speckle to change nearly as much. A system like this allows us to get focal stacks with with very low speckle. And like I said before, it's much more robust to optical aberrations. So this is another example from the paper of the experimental prototype, which is basically speckle-free. So this was pretty exciting, and I think a lot of people were really interested in seeing how these holographic displays were starting to finally get to image quality that looked to be on par with a traditional display. We're starting to make progress and starting to get to the point where you might actually want to look at these things. I was super excited about this. I started doing a lot of work in this field. I started building prototypes and looking at them myself. And then I started having some doubts. Unfortunately, when I started looking at these, I was worried they didn't look as good as I was hoping. And some of the clues that were pointing to this were things that we might have been able to see before. If we go back to this picture, you might notice that the out of focus light sort of has this unnatural ringing. It doesn't truly look like a nice bokeh defocus blur like what we see in a regular photograph and what we see on our eyes when we look at the real world. You can also see this in the simulation I showed earlier. So right now this is focused on the foreground. But if we take a look at this robot in the background, you can see that there's all of this ringing that has these high frequencies, that normally things that are out of focus don't have high spatial frequencies. And compared to the target, to what we wanted to show, there's actually less defocus than we'd expect. If we take a look at what these smooth holograms are really doing, this isn't too surprising. It's the random structure of the diffuse surface that scatters the light to higher angles, and this allows us to get better focal cues because that light is a full cone that's going into your eye that's integrated over your whole pupil. We also have a problem in smooth holograms where if you move your eye by a little bit, because the light is not scattered very far, we can quickly lose the image. And in addition, all of that light gets concentrated in a small part of your pupil. And so that means if there's any defects in your eye, like floaters that most people have, or pieces of hair, or eyelashes, or scratches on your cornea, all of that gets really amplified. As we're in real life, we're generally averaging over the whole pupil, so those sorts of defects are a lot less noticeable. So that was actually one of the first artifacts I noticed when I was looking at these, was that like little pieces of hair were creating all of these distracting ringing artifacts. And at first I told myself like, well, this is okay. You know, if there's dust in the system, we'll just clean it better. Like, you know, this is a problem because I wasn't very careful. But at some point I started to realize like, eyelashes are kind of fundamental, and maybe if they're creating artifacts, that's a real problem. All of this was confirmed in this user study that was done in 2022, which was one of the first user studies in holographic displays, where they tried to measure how well people were able to accommodate or focus their eyes on holograms made with different algorithms. And these smooth holograms, which are the yellow bar to the far left, did a much worse job of driving human accommodation than even those really speckly holograms that I showed you before. So it's starting to look like maybe these smooth holograms weren't quite in the right direction that we needed to go, and we need to go back to the drawing board and figure out how to deal with the speckle problem. So we can look in our bag of despeckling tricks, and one that comes up frequently is this idea of temporal multiplexing. Basically, we're going to show in fast sequence a bunch of different instantiations of the image that each have different speckle. So basically, we'll have a different object surface for each one. And if we show these fast enough, due to human persistence of vision, these get averaged together, and that reduces the speckle contrast. This is pretty effective, and here's a simulation. So you can see that we're able to get our nice focal cues with the right amount of focus blur, and the speckle is greatly reduced. We also get to keep all of those advantages of the random holograms without having sort of these artifacts from hair or limited focal cues. Some of the best holographic displays that I've seen to date are doing this technique. They're basically using the fastest modulators available and trying to reduce speckle in this way. However, they're still not speckle-free. And one of the challenges we get is that the amount of speckle reduction goes with the square root of the number of frames. And so we need to have increasingly faster modulators in order to get speckle reduction even higher. As we go to faster modulators, though, we start to have more problems with data bandwidth. It starts to feel really inefficient as we start to, it's just hard to run a display like this at tens of kilohertz that's like maybe a 2 megapixel display. You quickly just use up your data bandwidth. So I'd like to tell you about a recent project that I worked on to try to improve speckle reduction without using temporal bandwidth. So this is something that can be combined with the temporal multiplexing technique, but hopefully gives us more avenues to try to reduce speckle and make these displays look like they have good image quality. So like temporal multiplexing, the idea here is we're going to try to create different versions of the speckle that get averaged together. But instead of doing it over time, we're going to do it over space. So if we add in different light sources at different angles, these are going to illuminate our modulator from different positions, and each of those therefore creates their own speckle pattern. Now the idea is that when we turn on all of these at once, they should get averaged together, once again reducing the speckle contrast. Of course, it's not really that simple, because if we're displaying an image of an object, then geometrically, if we illuminate by a different angle, that light hits the modulator in the same place, it sees the same pattern, but now geometrically the object appears at a different location. So if we turn on all of these sources at once, we're going to create a bunch of doubling or blurring in the image. Even if we try to optimize our display knowing that this is going to happen, it's a really poorly posed problem, and so we're not able to create good image content everywhere, at least for arbitrary scenes. So this is sort of the best attempt at doing this, and it doesn't look very good. The problem here is that each of these different light sources is essentially seeing the same display. Ideally, we would like to have some amount of angular selectivity to our display. And one way we can do this is going back to the idea of having a more volumetric modulator. So in an analog hologram, we had a volume that we can modulate over, which actually allows us to have angular selectivity. In this case, we still are stuck with our controllable panels, but if we put two of them with a small gap between them, this allows us to have a different pattern for each of these different sources. So you can see that geometrically, essentially each source is seeing a different translation between those two modulators, which allows us to effectively independently control what each of the light sources is creating. We can use that to try to line up all of these different images so that when all the light sources are on at once, we don't get any doubling, but we still get the speckle reduction. So this is what this looks like in simulation, focused on the background, now the middle, and now the foreground. And you can see that this looks pretty similar to the temporal multiplexing result, but this is all done in one time frame, and we only need 2 modulators worth of data instead of 8 to 20 that we were using in the previous cases. So this seemed pretty promising. So to experimentally validate this, we built this cool multi-source system. This has 16 different sources that are all held together in this 3D printed housing. And we tested this out on this benchtop setup that let us toggle between that multi-source configuration and the more traditional single source. So here's an example of a hologram taken with a single source, and the calibration has improved a lot from that house image I showed you earlier. Things got a lot better in the 3 years between those things, but there's still speckle. And when we use the multi-source configuration, by averaging together all of the contributions from those sources, we get some nice speckle reduction. Here is another example of my co-author Florian's cats. But all of this becomes even more apparent when we move to 3D scenes. So this is a scene where we are focused right now in the background, and this middle plant, and now this plant in the front. And when we move to our multi-source configuration, we get significant speckle reduction and a lot of improved contrast, because it turns out that speckle was reducing the black level. Here's another example where, once again, with a single source, it's almost difficult to see the changes in focal cues here because the speckle hides those cues so much. But with the multi-source system, we can get our speckle reduction while keeping those nice focal cues. So we might have gone on a bit of a detour with these smooth phase holograms, but hopefully from this, we're able to learn things and move on and be able to create something that's even better. I think a lot of research really has this sort of non-linear path, and especially in my work in holography, I feel like that's been particularly true. There's sort of been this meandering course of pushing on all of these different aspects and trying to figure out how they can come together to really make something that is the ultimate display. Sometimes, though, it's a little unclear where we're truly going with this work. Is it just these one-off papers that push on some specific axis? that push on some specific axis that makes one thing a little bit better, but maybe at the sacrifice of something else? So I'd really like to take the last bit of this talk today to tell you about my vision of the future of holographic displays and where I really think that we're going with this, trying to be honest with myself about what I think this technology can actually achieve. So for any technology to be successful, we have to have advantages that outweigh the disadvantages. In holographic displays, some of the advantages that get cited the most are, of course, these 3D effects like focal cues and parallax, the ability to potentially make a super compact form factor, because we're doing this all in a single plane. Some other things that come up are the ability to do prescription correction in software. So potentially if you wear glasses, you could program in your prescription, and then you'd be able to see a sharp image without wearing prescription correction. And holographic displays tend to be higher optical efficiency than more traditional counterparts. But all of this comes with some severe disadvantages that we've already seen, like the speckle noise, reduced contrast, and increased computational complexity. And to be brutally honest, even with all of the research that we've done on trying to reduce speckle in these images, the image quality still isn't on par with existing screens like your cell phones or your computers, or even a VR headset. Yes, we add in additional effects like focal cues, but these are things that we can add in other ways. In a VR headset, we can change the position of the screen or the positions of the lenses to create focal cues. And so that's a much more mature technology that doesn't come with all of these disadvantages in image quality. So I actually honestly do not think that focal cues are going to be the thing that's the driving factor for holographic displays, because I think that if that's all we care about, there are other better ways to do it. Similarly, I think that prescription correction and optical efficiency are nice to have, but they're also not things that are going to make this worth the disadvantages. So what I really think the driving advantage of holographic displays is going to be is in form factor, the ability to make something really small and compact, which is especially necessary if we're building head-mounted systems, because we really care about like every square millimeter if this is something that's going to be on your head. Now, of course, it doesn't matter how small something is if we don't like looking at the images, why wear it in the first place. So we do need to have some sort of minimum image quality. But I think a space where image quality is a little bit less important is for see-through systems, like AR. So in these systems, we're overlaying an image on top of the real world. And so in this case, we're not seeing the image fully by itself, and it's sort of like a more immersive, like watching a movie setting. We already have some reduction in image quality because it's overlaid with the real world. So this is an example of an old holographic display I worked on in an AR mode. And this has a bunch of speckle, there's a bunch of background haze, but it's less noticeable because we're looking at it over a real scene. So with this in mind, where I really think that holographic displays are going to make a big impact is when we do this in glasses form factor for AR systems. And I think that I have a pretty compelling story about how we can get there. Now, making things in glasses form factor is really hard because glasses are really small and there's just not very much space on them. One of the things that we want to put on a glasses system, if it's an AR system, is some sort of display engine, some sort of projector or display. And to have this fit in the glasses, it has to be really small. Now, this means that we can't fit very much light inside this display. There's a concept in optics called étendue, which is a metric of how much light is in a display and is correlated with the size. And so when we have a small projector, we have very limited étendue. The problem is, once we send this light to your eye, we would like this to take up a lot of space. We'd like this to cover a large range of angles, to cover a large field of view, and we'd like it to cover a large area, because that's where you have to put your eye in order to see the image. So any glasses form factor display has to deal with this problem of how do we expand the light from a small projector to cover this large area when we actually get to the display. The way most AR systems do this today is with waveguides. So the idea is we're going to take a small projector, we're going to couple that light into a waveguide where it propagates based on total internal reflection, and then it's going to outcouple later in the system. When it outcouples, some of the light is going to bounce towards the eye, and some of the light is going to keep going through the waveguide. And at each of these bounces, the light is split. And that splitting is what increases sort of the area that the light can cover in this system. So this effectively takes our small projector with a small area and allows us to spread that light over a large area. Waveguides are really elegant. I think that they're a really beautiful concept, but they do have their limitations. And one of the notable ones is that light can only travel through it if it meets the TIR condition. So there's only a limited range of angles that can propagate through this, and in the end, that limits the field of view at the output. This makes it really hard to get very immersive fields of view with these sorts of systems. So how can holographic displays help with this? Well, waveguides do this replication in a very ordered way that works well with traditional systems. But in holographic displays, we have a lot more control over the light, so we might be able to use other ways for expanding the light to cover this larger area. One proposal is to do this with a diffuser. So like the diffusers you might put over a light, they're really good at scattering light to higher angles. But they're also really bad at making a display, because if you hold up a diffuser in front of a traditional screen, like my laptop screen here, there is nothing you can display on that laptop screen so that you get a sharp image when you look through this diffuser. However, with a holographic display, where we have control over both the phase and amplitude information of the electric field, and we can control the light with much finer grained control, we can actually start to control the light so that we get the scattering properties of the diffuser, but are still able to form a nice image on the other side. So here's an optical system to test out this idea. We have our display, our spatial light modulator, and our diffuser here. And then this is actually a human viewable system with an eyepiece, so you could look inside of it and see the image. But I'll show some images taken with a camera on this system. So it turns out that with the right calibration and the right processing, we can form an image through this diffuser, and this is what we get. So it's a pretty good image compared to what we were trying to make. There's a bit of contrast reduction, a little bit of speckle, but it's pretty high resolution, the contrast is fairly good, and the quality looks pretty nice. And this is through this diffuser. Now, this was not easy to get this image. The first time I actually tried to make an image through this diffuser, this is what I actually captured. This is the same image of that same house. I use that image all the time for some reason. If you can't see the house in this image, you should probably squint harder because it's there. I can see it. In all seriousness, though, the challenge here is that we need to know that diffuser surface with really high accuracy, with sub-wavelength accuracy, in order to be able to control the field so it looks like an image after passing through it. And if we don't have an accurate model of what's happening, we end up with something like this because of that discrepancy between the simulation and real life. In order to overcome this, what I ended up doing was putting a camera in the system and collecting a large data set of pairs of displayed images and camera captures, and slowly using that to refine our model of what was happening at that diffuser surface. And each time we refine the model, we get a better, more accurate simulation of what's happening in real life, and this allows us to start doing a better job of creating the images we want. So, as I said before, this is a human viewable system. It had a field of view of 55 degrees and a 5mm eye box. So 55 degrees is decent for AR, but it's not earth-shattering. There's AR systems that are as good or better than that. 5 millimeters is a bit small for an eye box. And this was all with a 25x increase in étendue. So basically, we're scattering the light to 5x the size in each direction in order to achieve this. Now, we were actually able to take this and artificially limit the amount of light coming from the projector in order to simulate what would happen with even more expansion. So here's an experimental capture now with 100x, so 2 orders of magnitude expansion in étendue. And so this would allow us to push those numbers towards immersive 90-degree fields of view with eye boxes that are of usable size, potentially on the order of 8 to 10 millimeters. So I showed that we're able to make images through this diffuser, but you might be wondering how this achieves our idea of doing glasses form factor AR. The proposal is that we're going to put this diffuser on the surface of the glasses. So we'll have our tiny projector off to the side, illuminating this diffuser, and when the light hits the diffuser, it's going to scatter to this larger range of angles, allowing us to fill out that large field of view in eye box. Of course, if we actually just put a diffuser on the surface of your glasses, you're not going to be able to see the real world very well. And so the idea here, which I think is pretty cool, is instead of actually using a real diffuser, we're going to print an analog hologram of that diffuser in the glasses. And the advantage of this is that that hologram is only sensitive to light of certain wavelengths and angles, and so we can design it to be only sensitive to light from the projector, allowing light from the real world to pass through unaltered. This is super early work, but here's a first image of this printed holographic diffuser. This is actually using a microlens array as the diffuser itself, so you might be able to see little dots from the microlens array structure. And you can see that we only see green light reflected because it's only sensitive to green, and we only see it at certain angles. So we can use this to both scatter the light from our projector while letting real light from the real world come in unscathed. So here's the initial setup to test out this element. So we have our illumination, we're going to hit our SLM. We have a mirror to bend this in at that sort of more extreme angle that we want for this off-axis system. And then we're going to capture this with a camera to start. I was really hoping to have some cool images to show of this, but this is super like bleeding edge work. The calibration is not done yet. This does not currently work. So I'm super excited to be able to share something that is ongoing. So I think that even though we've had a lot of ups and downs in holography, I'm really optimistic about where we're going. I think that we can take holography to enable some really cool things in displays, especially as we're pushing on form factor to make things really compact. And with that, we're a little over because we started a little bit late, but hopefully I have some time to take some questions.